first, right?
Sure.
Hi, Shweta.
Hi.
Okay, yeah, please go ahead, Vinod.
Thanks, Umang. Welcome, everyone. Today we have Shweta Agrawal joining us from IIT Madras. She is at the Computer Science and Engineering department there. Shweta has a bachelor's degree in computer science from Duet University, and she has a PhD from University of Texas at Austin. In fact, she worked on both information theory and cryptography at Stanford during her PhD. She was a postdoc at UCLA with Sahai. She was at IIT Delhi in the computer science department, and then she moved to IIT Madras. So research interest, as you know, is in cryptography. And among other things, her focus has mostly been on, the particular focus has been on post-quantum cryptography. Notably cryptography, which is based on hardness of lattice problems. And she has won many awards for her work. Just last year, she won the Best Paper Award at Eurocrypt, which is a principal conference in the area of cryptography, and the Swarna Jayanti Fellowship from the Government of India. Okay, Shweta, tell us about cryptography.
Thanks, Vinod. Thanks to the, can everybody hear me just fine?
Yes.
Okay. So thanks to the organizers for inviting me, and thanks, Vinod, for the introduction. I'm really excited to be here. May I request the audience to turn on their videos just for a second so that I can see all the students who've joined us?
So let's all turn on our videos for just a minute, I guess.
Yeah, I think the part about not being able to even see whom you're talking to is the worst part of this online stuff. So I at least ask people to show themselves for like 1 minute before the talk. Okay, it's great to see everybody, and yeah, feel free to turn off your videos if your bandwidth is bad. Let me get started. So I'm going to talk about cryptography, the Jugalbandi of structure and randomness. So Jugalbandi is Duet, but it's also more, there's more fun into it than just Duet. And let me explain what I mean as I go forward. Okay, so let's start just with what is cryptography. And as you all know, after attending these great lectures last week, cryptography is the art of secret keeping, right? And we give strong mathematical guarantees that your secrets are safe. So what kind of guarantees do we give? Well, we say that we guarantee to you that breaking a crypto system is at least as hard as solving some difficult mathematical problem. And how do we give this guarantee? Well, being computer scientists, we do it via reduction. So we design an algorithm. Here we call it a reduction B, which takes as an input an instance of some hard problem. So your favorite hard problem from last week, factoring or discrete log or whatever one you liked the best, right? And then this reduction is going to massage this hard problem into a crypto system, right? And if there exists an attacker A who can find a break on this crypto system, then this attacker will return the break to the reduction B, who will massage it back into a solution to the original problem. So this guarantees that if there exists an efficient attacker against my crypto scheme, then there also exists an efficient algorithm breaking my underlying hard problem, right? So if I choose my hard problem well, then this is going to be unlikely, meaning that my crypto system is safe. And for the purposes of this talk, I'm going to take encryption as a case study. Okay, so this is in part because I'm just fascinated by encryption. I feel that this is almost the most basic thing that everybody thinks about. Like whenever I'm giving an outreach talk, I ask people, what does cryptography mean to you? And almost all the times encryption is what everybody thinks about, right? So, and it's still something we understand very little. At least I feel I understand very little. So let's take this as a case study, and the whole talk will be about this. So let me remind you what is public key encryption, although I'm pretty sure it's fresh in your mind, but still for completeness, right? So we have two users, a sender and a receiver, typically called Alice and Bob respectively, but here the genders are swapped. So let's call them Anant and Babita. Okay, so Anant wants to send a secret message to Babita, and she has published her public key. So she has generated a pair of mathematically related keys, a public key and a private key. She keeps the private key for herself. She publishes the public key. And he's going to use this public key to somehow encode or somehow encrypt this message and send her the resultant ciphertext. And she should be able to plug in her private key and open this locked box. Okay, so she should be able to recover the message. So the two things that you really want from this scheme are functionality, of course. I mean, you should be able to recover whatever your friend sent you, and you want security. So if there's a malicious person sitting and listening on this channel, then when they receive the ciphertext should leak no information about the message. So another way of thinking about it is that the ciphertext should be indistinguishable from a uniformly random string. Okay, so we want functionality and security. And a bit of thought shows that you're already walking a kind of fine line. These two requirements are sort of really in conflict, right? There's a tension between them. So I claim that getting functionality without security or vice versa is easy. Can anyone tell me how? So if I only want functionality and I don't care about security, how will I get it?
Then we simply pass on the message, ma'am.
Exactly. You can simply transfer the message. So, that's easy. And security is even easier. If I don't want functionality and I want security, what should I do?
I should not send the message even.
I should do nothing. Yeah. So it's very easy, right? Security without functionality is extremely, extremely easy. But of course, you want both, right? And that's what this talk is going to be about this inherent tension between them and how to make it work. So functionality, I claim, requires structure, some kind of structure. And security, on the other hand, requires randomness, the lack of structure, right? So getting both together, how do we do that? And in cryptography, we do this by choosing a suitable hard mathematical problem on which we base our system. So let's take as an example this problem, which is the closest vector problem on lattices. Okay, so this is an example of a problem in mathematics, which we believe is very hard. I'll define it for you in the next couple of slides. So before I tell you what is the closest vector problem on a lattice, I should first tell you what is a lattice, right? And a lattice, it's, you've seen lattices all over the place. It's a set of points with periodic arrangement. A little more formally, it's a discrete subgroup of Rn. And the simplest lattice in n dimensions is just the integer lattice, so z to the n, right? So these points, they're closed under addition, right? So if I take two lattice points and I add them up, I'm going to get another lattice point. And a little bit more generally, I mean, generalizing from the integer lattice, I can construct another lattice by applying a linear transformation to this integer lattice. So what can I do? Well, I can take a bunch of vectors over the reals. These are called basis vectors. And I look at all the points that are generated by taking integer linear combinations of them. Okay, so it's a discrete set, right? So I take only integer linear combinations of these basis vectors and I get a general lattice, right? And now in a general lattice, let us try to see what kind of hardness we can get. So where can we get our hard problems? The most famous problem in a lattice is the shortest vector problem. And what is this problem? Well, it's simply saying that if I give you a lattice as represented by its basis vectors, find for me the shortest non-zero lattice vector with some length. Let's forget what is lambda 1 here. Let's just say, I'm giving you some length that I'm happy with, some short length. Okay, so just the L2 norm of this vector should be short. And I can specify as a parameter what this short means. Okay, so I'm giving you this lattice represented by a basis, and I'm asking you to find the shortest non-zero lattice vector in this lattice. Shortest non-zero lattice vector, full stop, right? So this is the shortest vector problem. Are there any questions about what we've seen so far?
No, ma'am.
Yeah, go on.
No questions, ma'am.
Oh, no questions. Okay, yeah, I should have said before that please feel free to stop and ask questions anytime during the talk. It's always more fun that way. Okay, so this is our shortest vector problem. And we can relax this problem a little bit. So maybe I will tell you what is lambda 1. So for any lattice, lambda 1 is the length of the shortest vector in that lattice. Okay. So if I ask you for a lattice of length lambda 1, I'm asking you for the shortest vector in the lattice. But I can relax. I can relax this a little bit and ask for a vector which is not the shortest, but approximately short. So that would be the approximate shortest vector problem. Okay. And then another problem, which is very interesting to us and which I alluded to earlier, is the closest vector problem. So here, once again, you're given a lattice, and now you're given a target point T. So this target point T is just a arbitrary point in space, and you're asked to find the closest lattice vector to this point. Okay, so you're asked to find the lattice point such that the distance between the target point and the lattice point is as low as can be. This is the closest vector problem. And we're going to see how these problems come up in cryptography. So let's try to build some crypto, right? Now, as you've already seen, the most basic thing that you can build in cryptography is a one-way function. So here is a function. It maps from some domain D to some range R. And we want this to be one way, which means that we want it to be easy to compute in the forward direction, but we want it to be hard to compute in the reverse direction, right? So it's one way. And as I already said, this is the most basic primitive in crypto. So let's see how to use lattices to build this. Okay. So first of all, I should tell you that in cryptography, we use particular types of lattices. We use random lattices. We want these lattices to be easy to sample, right? Because cryptography is constructive. So we need to actually be able to generate this lattice and whatever short vectors or whatever it is that we want, we need to be able to generate them. So let's at least pick a suitable lattice. And what we use typically are random integer lattices that are periodic modulo some integer q. So for simplicity, you can think of q as a large prime. Okay, and we're going to use what are called query lattices, which only involve arithmetic modulo q. Okay, so a lattice lambda is a query lattice if QZN is contained in lambda and lambda itself is contained in Zn. Okay, and the two particular lattices that we're going to be interested in are the following. So first we define this lambda q of A, which is defined as A transpose times ZQ to the N. So all points that can be written as A transpose ZQ to the N. Okay, so you're taking all integer combinations of the columns of A transpose or the rows of A. So this is one lattice that we like. It's easy to see that this is a lattice, right? If I take 2 points x1 and x2 and I add them, then I'm again going to get something that can be written as A transpose times an integer vector. Okay, so this is one nice lattice which we like. And another one is actually it's dual. So dual there is a way to make it precise, but even just the natural meaning of the word dual, right? So this is called lambda perp QA. Okay, so this is the set of all vectors x such that A times x is 0 mod q. All right, so these are two lattices that we like, and I'm going to show you how to get one-way functions from these. Is that good? Are there any questions?
Shweta, this is Jaykumar.
Yeah.
So these lattices are infinite, even though they are query. It's not as if we are only dealing with numbers 1 to 2.
Yeah. That is true. Yes, they are infinite.
Thank you.
Okay, so let me tell you about
Prahlad here. Can you go to the previous slide? So what does Q at the, just for notational, what does Z with a Q at the base, what does that represent as a subscript?
Z with the Q at the
so
base.
it's in the definition of lambda Q of A.
So you have Z and Q. So what does that?
ZQN. Yeah, ZQ. So 0 to Q minus 1.
0 to Q. Okay.
Yeah. All right. So let's keep going. So let's look at a one-way function. So this is a famous one-way function discovered by IITM. So here what we're going to do is we're going to sample a random matrix A, and this is going to define a lattice implicitly. I'll show it to you in a second. It's of course related to what we saw in the previous slide. And the input to this function, so I'm defining a one-way function. So the function will be parameterized by this matrix A, and the input is some vector x, which is short. Okay, so think of it just as a binary vector for now. It need not be binary. It just needs to be short, but let's think of it as binary. So my function is simply AX mod Q. That's it. So I just take the matrix vector product of A and X, and this is the output of my function. Now, it is obvious that the restriction of X to be binary, or more generally to be short, is very crucial here, right? Because if I don't have any such restriction, then I can easily, given A and given AX mod Q, I can always find some candidate X with large entries just by Gaussian elimination, right? But it turns out, and it was shown by IITM, that for appropriate parameters, if lattice problems are hard to approximate in the worst case, so this is amazing, right? So in the worst case, then FA of X is a one-way function. So you're getting a pretty strong guarantee here. You're getting a worst case, average case connection. And this is why this result was very celebrated, very surprising when it first came out. Now, we don't have time to get into this proof in this talk, but I just want to hint at, how lattices are lurking around here. So remember, we saw this lattice, right? So lambda perp of A, which contains all the vectors X that are orthogonal to A mod Q, right? So now FA of X is nothing but AX mod Q. So if I think of the output as 0, so if I think of FA of X equal to 0, of course, for random X, it's not likely to be 0, but just for a second, if I think of it as being equal to 0, then I'm asking for a short vector X in this lattice. right? So this should be hard because of the shortest vector problem. Does that make sense? It's very hand wavy, but just to get a sense of what's going on.
Sorry, this connection I didn't see. Why is this equivalent to finding a short vector? Can you just go over that once
Just
again?
because, so x is in the lattice, right? And x has low norm. So if given A and given AX mod Q, if I can find a low norm x such that it satisfies the equation, then I'm essentially asking for a short vector in this lattice.
Okay.
Right? And now let's look at another function related to our other lattice that we saw. Okay. So this is Regis one-way function. This function, I mean, in a way, this work and this line of work is, what's kept me off the streets. So a lot of my work is just based on this one paper and this, this one-way function that I'm showing you. So here, how do we define our function? So G sub A over here takes as input some vector S, okay, and now S is multiplied to the it's multiplied on the shorter side of A. So this is important. So this is going to be an injective function. So S is multiplied on the shorter side of A, and then actually a little bit of error is added. Okay, so again, we can think of the error as being just binary, but again, it need not be binary, but it's a good intuition to have. So GA S comma E is defined as AS plus E mod Q. Okay, and the one-way function, which is, or the underlying hard problem, which is called the learning with errors problem, is that given A, the function description, and the output of the function on some point, you recover that point, right? So given A and GAS comma E, you recover S. And Regis showed that if this function is hard to invert on the average, he showed that this function is hard to invert on the average, assuming that lattice problems are hard to approximate in the worst case. So now if we look at our other lattice that we saw, right? So this is the set of points that can be written as A times a Z vector, right? Then you can see that AS over here, AS you can think of as a lattice point, right? So this little bit of error that is added to it means that you're perturbing the lattice point a little bit, right? So this is like the closest vector problem, again, in a very, very hand-wavy way, right? So not only, it turns out that not only is it hard to find this, it's actually hard to distinguish this perturbed lattice point from a uniformly distributed point. Okay, so this is the second one-way function that I wanted to show you. And based on these two, I want to show you an example encryption scheme. So are we all clear about these two one-way functions? So the first one is simply given a matrix A, I'm just computing AX mod Q. Here, X is multiplied on the fat side of the matrix, okay? And the second one is that given a matrix A, I compute AS and I add a little bit of error to it. Here S is multiplied on the short side of the matrix. All right, so these are our two one-way functions.
Does Q have to be prime or it can be any number?
Actually, so you can think of it as prime, but in fact, Q can be, there's a lot of flexibility in how you choose Q. So pretty much any Q ends up being okay for this problem.
Shweta, so just to understand Regis one-way function.
Yes.
So picking up S is like picking up a lattice point, this one, and then adding E is to sort of fudge it a little bit to move around the lattice point.
Yes.
So what do we, so basically, so the output of the one-way function is not the lattice point, but some point close around.
Yes, yes.
What's the distribution on E that we need to ensure that this is actually an injective map?
So the distribution of E, well, really speaking, we want E to be short. So it's a vector. We want it to be short. There is again some flexibility in how you choose the distribution of E. But I should say here that, okay, first let me answer your question. There's flexibility in how you choose E. So the most standard way of choosing it is actually from what's called a discrete Gaussian distribution. So it's a Gaussian distribution, but discretized 2 points in the lattice.
Okay, so it is mostly one way. It's mostly injective, not always injective. So because of the E could have picked up things which are far away.
Yeah, that's true. That's true. I should have said that. Yeah. There is some probability that your E was huge because when you sample it, I guess it depends how you sample it. So if you're sampling uniformly from 0, 1, then, not much chance of being large. But typically we sample it from the discrete Gaussian distribution, and then there is some probability that your E will end up being large.
Thanks.
That's a good point. Yeah. Any other questions? All right, so let me show you our first encryption scheme. So as we just saw, we have this one-way function, right? AE mod Q. So I'm sort of changing X to E here because I might use X for something else. So AE mod Q is hard to invert, okay? So let's say that during key generation, what I do is I first sample my matrix A of the right size, and then I sample a short secret E, and I compute A times E, okay? And I denote this by U. So now what's public here is A and U, and what's secret is E, all right? Now, and I mean, obviously, because this function is one way, I cannot recover the secret from the public key. I can't. So that's a basic sanity check. I mean, you should at the very least not be able to recover the secret key from the public key. Now, how do I encrypt? Okay, so in order to encrypt, I'm going to leverage Regis one-way function that I showed you in the previous slide. So what I'll do is, well, I'm given my public key A and U, and I have some message. Let's think of this message as a bit. So now I'm going to just pick a random vector S, and I'll compute the matrix vector product of AS and add some noise to it. So this transpose here is because I'm thinking of A here as a fat matrix. Maybe I should have drawn it. So remember that S gets multiplied to the short side of the matrix, right? So you could also have written it as SA. Anyway, so my ciphertext is A transpose S plus some noise, as well as U transpose S plus noise plus the message bit scaled by half the field size. Okay, we'll see why that's important. And now, how do I decrypt using my secret key? So naturally, since I have that A times E is congruent to U mod Q, and I have an A and a U hanging around over here, and this is the only relation between them, pretty much the only thing that I can try doing here is multiplying E with, the stuff that contains A, right? So E transpose C0. So what's E transpose C0 going to give me? Well, E transpose C0 is E transpose A transpose S, which is nothing but U transpose S, plus E transpose noise, right? So I get U transpose S plus E transpose noise minus C1. So the U transpose S gets cancelled out. And I get left with Q over 2 times the message plus this noise plus E transpose that noise, right? Now the main point here is that this final noise that I got is only small if E were small, right? So I can only bound the value of this final noise if I know that my secret key is also going to be small. So this is why without a short secret, I cannot decrypt this ciphertext. So again, this is a basic sanity check, right? So just a little bit more about decryption here, right? So if my noise is bounded, right? So we look at this line here. So it's going from 0 to Q minus 1, right? Now, if my message is 0, then I'm going to sort of, and my noise is bounded. So let's say that my noise is only as long as this box here. Then Q over 2 times message plus noise is going to somehow hang around in this region at the bottom over here. Whereas if my message bit was 1, then Q over 2 times message plus noise is going to hang around, close to Q over 2. So as long as my noise is large enough that these two areas do not overlap, I can recover my message bit. Does functionality make sense? Does anyone have a question about why correctness holds? Yeah.
You mentioned that as long as an E is large enough that they do not collide. So E is a distribution.
Say that again, as long as?
Am I audible now?
Yeah, just it was a little, yeah, please go on.
Ma'am, you mentioned that as long as our E is large enough that the two regions do not collide, we can have functionality.
Small enough.
Okay, sorry, small enough. Sorry. So my question was about large E's. Like you said that there is a probability that we get E as a large value based on our distribution. So how do we ensure functionality then?
So E is part of our key generation, right? So basically during key generation, I'm going to sample my matrix A and then I'm going to sample E from the required distribution. If I get something bad, I could just throw it away. Or another way to think about it is that, there is some probability of decryption failure. But I mean, E is picked from a distribution such that with overwhelming probability, it is a short vector.
Okay, ma'am. Thank you.
Sure. Any other questions? All right. So what about security now, right? So we got functionality and sort of maybe I should emphasize, given the title of my talk, that the functionality here really crucially relies on the structure of the problem, right? The fact that you can write the ciphertext as some AS plus noise, US plus noise. This is what allows you a method to cancel the large masking factor and recover the message. What about security? Well, security follows from the random aspect of the hardness assumption or the pseudo-random aspect. So we know from the learning with errors problem that I showed you previously that this matrix times S plus noise, this looks uniformly random to an adversary. I mean, to any polynomial time algorithm, right? So what does this mean? It means that this message which I have is being masked by something which is pseudo-random, right? So it's this is acting like a one-time pad to protect this message. So therefore, by the security or by the hardness of this learning with errors problem, we have that this ciphertext is indistinguishable from random and therefore it protects the message bit.
Shweta, why is U random?
I chose, oh, very good. Yeah. So you can show that when I pick
This is
A,
this left or hash lemma, right? If you have E to be 0, 1 uniform, then A times E should be.
yes. I was trying to think if there was more to LHL than more to it than LHL, but let me just think for a second. Yeah, actually, I think leftover hash lemma suffices. So yeah, so basically for the parameters that we have chosen and for the distributions that we have chosen, you can show that U is going to be uniformly random. Yeah, that's a very good question. Thanks for asking. Any other questions? Okay, great. So we have our first encryption scheme, and the amazing thing is that the scheme I showed you almost directly gives what is called a fully homomorphic encryption scheme. Okay, so let me tell you what is fully homomorphic encryption. Well, so the idea of fully homomorphic encryption in one line is that encryption and function evaluation commute, almost commute. Okay, so if I encrypt some data, let's say I encrypt some value X, okay, and I want to compute some function f on this vector X. There's actually a way for me to compute this function on the encrypted data. So on the ciphertext, I can compute this function. So to be honest, I don't compute exactly the same function. I compute a closely related function f prime. So if I want to, compute f on the underlying data, I compute f prime, outside on the encrypted data. And this f prime or this function evaluation can be done by an untrusted cloud server. So this is one of the main motivations for fully homomorphic encryption, that you can encrypt your data and still do meaningful stuff with it, right? You can run your data mining algorithms on it. You can use it for medical research on sensitive data and so on. And amazingly, what you're going to get after this evaluation is encryption of f of x. So the function gets computed inside, okay? And then when I decrypt it using my secret key, I can get f of x in the tier. Okay, so the idea is that I encrypt, I compute, I decrypt. This is equivalent to just computing on the plain text directly. So I can compute on the encrypted data. And this was a big breakthrough in cryptography when it first came out in 2009. And I was a PhD student back then. And, this result was announced. I remember going to the talk, and I have to say that it was this that made me switch to cryptography. So before that, I was dabbling in many different things. But this result was just amazingly cool. It still is, and we've made a lot of progress since then. So the functionality that you get in this construction is very expressive. So you can compute an arbitrary polynomial sized circuit. And the amazing thing is that the size of your ciphertext does not grow. So you're going to end up with a ciphertext which is short, it's compact. It does not depend on the size of the circuit that you evaluated, or the number of ciphertext that you used for the evaluation. The final ciphertext is going to be compact. And as I already said, a clean way to think about it is that encryption and function evaluation commute. Are there any questions about this primitive?
What do we know about the functions for which this is true? Is there some class of functions or?
All poly-sized circuits.
Oh, okay.
Yeah, so it's quite general. All right. So as it turns out, as I told you, it's actually this same encryption scheme. So I already showed you key generation, encryption, and decryption. So all I need to show you is evaluation, right? And in order to show you evaluation of an arbitrary circuit, it would suffice to show addition and multiplication, for instance, right? Because you can use those two to get any circuit. And addition is very easy. You can see it right now, right? So if I have message 1 and message 2, I have a ciphertext for message 1 and a ciphertext for message 2. If I just add them, I'm going to get a ciphertext for message 1 plus message 2, right? Multiplication takes work. It's still, these days, it's simple enough that, in a 1 hour lecture, you can explain it. But we don't have, we cannot do it today, but it's really by now very, very clean and simple. So the original construction was very complex, but now we know how to do it in a very, very clean way. All right.
Shweta, so one quick question. So how does the circuit size feature in this at all? Does it feature only in the time that it's going to take? But otherwise it doesn't show up in any of the lengths?
Yeah, that's exactly right.
I see. Okay.
It's really sort of cool. So from plain learning with errors, which I showed you, actually there is another dependence, which is depth dependence. So, your public key will depend on the depth of the circuit. But if you assume a little more, if you assume what we call circular security, which means that, the encryption of the scheme's secret key is safe, then you can even evaluate arbitrary depth without it showing up anywhere.
Okay, thank you.
All right. So, so cryptography is, dancing the dance. It's a Jugalbandi between correctness and security, algorithms and complexity, and structure and randomness, right? And for the rest of the technical talk, I'd like to describe an extension of fully homomorphic encryption that we recently worked on, which includes a fascinating notion called deniability. Okay, so let me tell you what this is. Okay, so I'm going to show you something which is both a deniable encryption scheme as well as a fully homomorphic encryption scheme. And this is joint work. I wanted to show you something which is very, very current. So this is some work which is going to appear in the upcoming crypto. So it's not even published technically yet. And it's also fitting for this audience because it's joint work with Shafi Goldwasser, who's an icon in our field and a role model for all of us. And student Salit Mosel, so a bright young student, just like all of you here, right? So I thought it was fitting that, in a women's audience, in a Vigyan Vidushi talk, that we should see a work which has these two authors. Okay, so let me show you what is the notion of deniable FHE. Now let's say that it's voting season and you have these two candidates represented by bits 0 and 1. So there's, as usual, there's a public key, secret key. The secret key is kept secret. And now to cast a vote, a user encrypts his vote, so he runs his favorite encryption, he runs the encryption algorithm specified by the voting protocol. He picks some randomness 0, he chooses his bit, and he produces a ciphertext, which he sends to the cloud. And all the other users in the system do the same thing. So now, you have all these ciphertexts. And now you would like to compute various things, right? So in particular, you would certainly like to compute who the winner is. And if the scheme supports homomorphism, then of course you can evaluate arbitrary circuits on it. So you can do evaluation. And you could decrypt on this evaluated ciphertext to learn who's the winner without decrypting any of the underlying ciphertext, thus maintaining the privacy of individual votes. So this is so far, I've just told you how homomorphism might help in a voting scenario. And indeed, what I showed you is very trivial, but modern voting protocols often use homomorphic encryption in sort of more sophisticated ways. But now let me bring in this notion of deniability. So here's the thing, right? So now let's say that we have another user and she has some sort of power over Bob. Okay, so she asks him, well, for whom did you vote? Now, one thing he could do is he could reveal his message bit and his randomness, right? And she can check that, encryption, with PK, B0 and R indeed gives the published ciphertext CT0. She could check this. But if he does not want to reveal his true choice, what he could do is he could run what is called a faking algorithm. And this faking algorithm is going to allow him to sample a fresh randomness R prime, a fake randomness, so that the opposite bit, so B0 bar with this fake randomness R prime, nevertheless gives the same ciphertext. Does that make sense? So it's a randomized algorithm, right? So basically, what I'm saying is that I can flip the message bit and choose a fake randomness to explain the fake message with the fake randomness to get the same ciphertext. And the distributions will all match up. Okay, so CT0 can be written either as an encryption with B0 and R, or B0 bar and R prime, where R prime is this fake randomness. Okay, and the two distributions will match up. Okay, so in particular, R prime and R are going to be from the same distribution. So the fake distribution and the honest distribution are going to be indistinguishable.
So Shweta, how is then correctness ensured? So if you decrypt the ciphertext, don't you?
That's a very good question. So you're losing a little bit in correctness. So you cannot have perfect correctness and deniability at the same time. You'll have to settle for correctness with overwhelming probability, and there's a negligible probability that correctness fails. And basically, the random strings for which correctness can fail, you're finding a way to sample from there to give the fake randomness.
Shweta, question. The randomness that is used in the original encryption when Bob is voting, is that just private randomness or is that public randomness?
No, it's private, right? So, I mean, randomness had better be private, because if my randomness is not private and my ciphertext is also not private, then my vote is not private.
So this is private, it's just known to Bob. It's not known even to the voting agency.
No, it's not known to anybody. And I mean, I should emphasize that is a standard thing in an encryption scheme, right? Your randomness is never known to anybody. So the whole idea here is that now someone puts a gun to my head and says, okay, show me what randomness you used. I'm going to show some different randomness, which will convince my coercer that actually I produced the ciphertext using a different message.
Swasti, do you want to go ahead since you raised before me?
Okay, thank you. Ma'am, so how would non-repudiation work in this? Like Bob can easily say that he used a different randomness. So how would non-repudiation work in this specific election example if you take?
So can you remind me what is non-repudiation? So it means that I should not be able to deny what I did.
Yes.
Yeah. So this is the opposite thing. So that's the thing in cryptography, right? Everything is a feature. I mean, this is for cases where you want to be able to non-repudiate, or you want to, you want to be able to deny.
Okay, because like what we have usually seen that cryptographic systems or like specifically digital signatures are non-repudiation. Non-repudiation feature is there, and here we're doing the opposite.
No, but see, these things are actually not in conflict, because the question is who's the adversary, right? So in a digital signature scheme, you have an adversary who's trying to forge your signature.
Yes.
Okay, now in this scenario, in the current scenario, maybe a nice example is, during the independence movement in the freedom struggle. Let's say, you're one of the freedom fighters and you want to organize a meeting. And now there is somebody from the police who comes and puts a gun to your head and says, open this message. So in that scenario, you want to be able to open it to something else. So I think the point, actually, let me go to my next or next to next. Oh, it seems I removed that slide. But what I wanted to, the slide I wanted to go to was going to say that this property actually encourages honest voting, right? It discourages vote selling. I mean, in our country, it would be great if we could discourage, in any country, I guess, it would be great if you could discourage vote selling, right? Now, why does it discourage vote selling? Because somebody comes and asks me, for whom did I vote? I can open it to anything I want. So there is no point for anybody to coerce me in any way, because they know that the encryption scheme does not support coercion. And, while on this topic, I want to say that this is exactly the paradoxical aspect of crypto that I just love so much. Like 10 years or more of being in this field, and I keep getting surprised at the kind of stuff you can do. Like for most of us, including me, when I think of encryption, right, I think very naturally of a commitment. Like I'm committing to something, I encrypt something, it has to decrypt, that means I cannot change it. But no, I mean, here is a way to change what, I mean, you are not changing what you did, but you're pretending you did something else. And you can get away with it. So the scheme I wanted to show you is fairly simple. I'm actually doing a bit badly on time. So Vinod, what time did we start exactly?
A little bit after 6, so we can take a little more time. Let us.
Shweta, it's entirely up to you. I mean, like I said, the session is up till 7:30. So whatever time you need, you want to give the talk, leave for questions, I leave that up to you.
Okay, so since I really wanted to show, I mean, I've gone slower than I had thought. I'm on my 19th slide, which is, I mean, I'm going very slowly, I guess. But let me show you all the main idea of what we're doing here, because as I said,
Shweta, can I ask a quick question? Because I think I'm very confused about something here.
Yeah.
So in principle, it's possible for every citizen to pretend as if they voted for some other person, right? I mean, like if it is the case that there is a gun held at every citizen,
yeah,
then how can you still compute who the majority is? I am a little confused because it feels like you've lost that information in the ciphertext. And whatever you're doing is a computation on these ciphertexts.
So why don't I show you the scheme, and you'll see that there is no contradiction there.
Okay,
right?
cool.
So basically what is going to happen is that the secret key is going to decrypt it correctly.
Oh, I see. So for someone who doesn't have the secret key, I see. Okay.
Only for someone who does not have the secret key.
Okay.
You can pretend that you computed this other thing, but with the secret key, it's going to decrypt correctly.
Okay. Yeah. Now I follow. Okay. Thank you.
Okay. Yeah. That was important. Thanks for asking. So yeah.
Once again to clarify, so the fact that these two fake distribution and honest distributions, they look identical to somebody who does not possess the secret key. That's what.
That's right. That's right. Yes. Okay. Yes. Yes. That's really crucial because, like you said, otherwise, how will you have correctness?
Thanks.
Yeah, that was really important. Maybe I didn't emphasize that enough. Yeah. Okay, so let me show you this scheme. So yeah, I mean, what I'm going to show you is something which has both homomorphism, so it has evaluation, and it also has deniability, so it has fake. Okay. And interestingly, I'm going to use homomorphism in a way to get deniability. So let me give you a very brief overview of how these FHE constructions work. Now, we already saw we saw a construction of a scheme which is in fact fully homomorphic, even though I didn't prove to you that it's homomorphic. But you saw that the ciphertext adds noise, right? The ciphertext has some noise in it for security. And a fact is that when I evaluate on these ciphertexts, okay, I add them, multiply them, whatever I do, the noise grows. And for the simple case of addition, you can see it already, right? So message 1 plus noise 1, message 2 plus noise 2, I add them, I get noise 1 plus noise 2. So the noise is going to grow. And after a while, it's going to kill correctness. Okay, so this, as it stands, limits the number of homomorphic operations that you can do. But Gentry, in his original proposal, the first FHE from 2009, showed a very clever way of how to keep going. Okay, so let me show you this very, very elegant idea, which is called bootstrapping. So let's assume that an encryption scheme is powerful enough or homomorphic enough to support evaluation of its own decryption circuit. Okay. Now, so by correctness of decryption, well, this is obvious, right? So if I decrypt ciphertext of X with secret key, I get X. I'm going to represent ciphertext by this red box. Okay. And what's sitting inside it is the message. So this is, just the decryption equation. Now I'm going to define a new circuit called DEC sub CT. So CT is hardwired in this circuit, okay? And the only input is actually SK. So I'm going to define DEC sub CT of SK as DEC of SK comma CT. So, I did nothing. It's just rewriting, just changing what the circuit is. So now I claim that if I evaluate DEC sub CT on an encryption of secret key, what do I get? Well, I get an encryption of the circuit applied to the input, which in this case is DEC sub CT of SK, which is nothing but X. So far, so good. Is this fine? Right, so I'm just running decryption circuit with a ciphertext hardwired in it. This circuit, I'm evaluating this circuit. This is my homomorphic computation on the encryption of the secret key. So by correctness of the homomorphism, I should get an encryption of f of x. So f here is DEC CT and x here is SK, right? So I should get an encryption of f of x. What is f of x here? DEC CT of SK. Maybe x was a bad choice. All right, so the circuit applied to the input here is nothing but the decrypted value of the ciphertext. Is this clear?
Shweta, have the arguments flipped in the green thing? The secret key in the circuit, should it be the other order, or is it that is the order you want it to be?
Yes, yes.
Okay.
It's crucial, in fact. Yeah, so I'm eager to show you what we do. Okay, so this idea was originally introduced to reduce the noise in the evaluated ciphertext, right? And why does it reduce noise? Well, I'm doing a homomorphic decryption. So that means I'm throwing away the old noise because decryption throws away the noise, right? I showed you the decryption. The decryption is the same. It's going to give me a bit, right? It's throwing away the noise. So when I do homomorphic evaluation of decryption, it still throws away the old noise. And it does add some new noise because of the homomorphic computation. But this is small because decryption is shallow. Okay, so what we do is we're actually going to use bootstrapping for oblivious sampling of FHE ciphertexts. Let me show you what I mean. So let's assume that decryption always outputs 0 or 1. This is easy to ensure. Even if I give the decryption circuit a garbage input value, a garbage ciphertext, I can ensure that, you know, if the ciphertext is good, it decrypts correctly. If the ciphertext is bad, it just always outputs 0, let us say. So this means that bootstrapping should always output a proper encryption of 0 or 1, because if decryption always outputs 0 or 1, then homomorphic evaluation of decryption should output an encryption of 0 or 1. So this is what we're saying, right? This is from the previous slide, right? So here what I'm saying is that even if this input CT is a random element in the ciphertext space, I'm still going to end up with the proper encryption of 0 or 1. And what I'm actually going to do is I'm going to bias this decryption to 0. So whenever the ciphertext is not well formed, I'm going to output 0. So bootstrapping will output an encryption of 0. Is this idea clear? This is actually almost all the idea that I wanted to show. Is this idea clear? So if decryption is always outputting a proper message, then homomorphic evaluation of decryption is also always outputting a proper encryption.
Can we just go over this again? Sorry.
Yeah, sure. So this is what we're saying. Actually, this slide is good enough here. So is the first bullet clear? So we're saying that decryption, regardless of input, you give me a good ciphertext, I will give you like the proper message, 0 or 1, whatever you encrypted. You give me a junk ciphertext, I will give you 0.
Okay.
So decryption is just an algorithm I design. I can insist that the only output you ever give me is either 0 or 1.
Okay,
great. So now what am I doing? Now remember, so this is why hardwiring ciphertext or CT in this decryption circuit was important. Because this CT could be junk. And what I'm doing here is I'm decrypting junk. I'm doing it under the hood of homomorphism, right? I'm doing it while I'm still encrypted. But basically I'm decrypting junk. But no problem, right? Because I insisted that even a decryption of junk is proper. It's always 0. Let's say, in fact, what we use is that you can test whether the ciphertext is well formed or not. Anyway, you have the secret key. If the ciphertext is garbage, I will always...
Is this going to always return 0 in,
yes,
in those instances?
Yes.
Okay,
so I will always return 0. And the well-formed ciphertexts are actually sparse in space. So if I pick a random element in the ciphertext space, this decryption is with overwhelming probability going to give me 0.
That's right. Yeah. Okay,
so even if the input is random, it's going to give me a proper encryption of 0. And the reason the encryption is proper is because the encryption of SK is proper. So by correctness of homomorphic evaluation, it doesn't matter what the circuit is. The fact that the ciphertext I'm evaluating on was properly generated means that the circuit must get evaluated properly. Is it fine?
So the when CT is random, so the decryption circuit might be some bogus circuit, but nevertheless, no.
The decryption circuit is a good decryption circuit, right? I mean, There's no malice in choosing the decryption circuit. The decryption circuit is an honest circuit. And what we're saying is that we modify this circuit to say that if the input is nonsense, output 0. That's it. If it is not nonsense, proceed as before.
So it's just that any nonsense ciphertext is always a valid encryption of 0 in some sense.
It is not by itself.
No. I mean, from as far exactly. Yeah, from the bootstrapping perspective, because of that, what you get at the end of it will always be some valid encryption.
Yes. Yeah. Exactly. So this is the picture for that. So if I give you random, right, and I run this bootstrapping, I'm going to get an encryption of 0. So I'm modifying my decryption circuit so that on random, it always outputs 0, which means that by correctness of homomorphism, the bootstrapping always outputs an encryption of 0. Okay, so yeah, we already said this. So I run bootstrapping on random and I get an encryption of 0 with overwhelming probability. But the cool thing is that if I did not start with nonsense, I get the faithful thing. If I start with an encryption of 1, bootstrapping maintains that this is an encryption of 1. Right? And encryption of 1 by property, by security of the underlying encryption scheme is in fact indistinguishable from random. Right? So when I run bootstrapping on CT1, which is a good encryption of 1, I get encryption of 1. And what I want to be able to do, I mean, in fact, what I'm going to be able to do is I can pretend as though CT1 is actually random. So this is how I'm going to fool my attacker. So I didn't show you the scheme and I'm running out of time, but let me just say that I can provide a randomness R so that it looks as though bootstrap of R gives encryption of 0, but actually what it gives is encryption of 1. So I'm already able to cheat in one direction. I can pretend to be 0 when in fact I'm 1. Of course, I need to do the other direction. And, I don't have time now to go into it, but basically I'm just going to take a large number of random strings, bootstrap all of them, and do their homomorphic XOR. So when I want to fake in either direction, I can just flip the parity by pretending that a particular 1 is actually a 0. This flips the parity. So now this lets me cheat in both directions.
So the ciphertext that you're bootstrapping, that is your randomness used in your encryption.
Yes.
That's what you can fake.
Yes. And the fact that I can sample the zeros obliviously as random strings is very important, right? If I were to encrypt 0 and encrypt 1 and run bootstrapping, then my attacker will say open the 0, open the 1. But because I'm saying, look, I just sampled it at random and it just ends up giving me an encryption of 0. Then because of that, later I can say, oh, actually this encryption of 1, which I sampled, which I not sampled, but I computed correctly, I can pretend that is random, thereby flipping 1 to 0. Okay, so I'm really very massively over time. So I'm just going to tell you that we can do it, from the learning with errors assumption. And in the minus 10 minutes that I have left, I will very quickly change gears completely. So the organizers suggested that this topic might be of interest for this audience. So let me just spend maybe another 5 minutes on women in science, okay? So yeah, I just want to maybe share a little bit of I don't know, a little bit of information or perspective on this. All of this is my personal take on the matter, right? So I'm no expert in gender studies, but I can just share a little bit of my personal experience and my personal challenges, and maybe it's going to be useful to somebody, one of you. Okay, so I want to start with a quote which appeared in this Scientific American article. The link is here. You can check it out later if you want. So whenever the subject of women in science comes up, there are people fiercely committed to the idea that sexism does not exist. They point to everything and anything else to explain differences, while becoming angry and condescending if you even suggest that discrimination could be a factor. But these people are wrong. This data shows that they are wrong. So clearly there is data here, which I am not going to get into. This has actually also been my personal experience. And there are studies, plenty of studies that show that this is, that discrimination is there. If you go to my webpage, I have listed a few links that you can look at to be convinced of this. Okay, so this is not my personal opinion. This is just data. So this is what the data shows. And a question that I would like to raise is, can we be open to this idea? I find that for all genders, in fact, many times it's difficult for us to just be open to this idea. Either we think we know everything about it, or we just don't want to deal with it. Many times, in fact, even women, we just don't want to deal with this thing, right? And other times we just reject it outright. But I think that it's good for us just to examine it. We're scientists, right? So what's the harm in just looking at things with an open mind? So I think that being open to this idea is useful and important, regardless of which gender one belongs to. In my opinion, and again, there is data, society does have biases, right? So a girl literally receives thousands of suggestions over time that tell her, that kind of put her in her place. My earliest memory is just the blessings that I used to get when touching feet of elders. So, age 5 onwards, my brother and I would go and we would touch people's feet. And the blessings he would get would always be, oh, be very successful. May you, have a lot of name and fame, stuff like that. And the blessings I would get would never mention any of that. So, I mean, I also got good blessings, right? In fact, maybe even better blessings, because I would get things like, may you always be happy. But the point is that I remember as a young girl noticing this, right? That somehow these are things meant only for him, not for me. And today I'm a faculty member at a good institute. Today I feel that, of course, now nobody is telling me what they were telling me when I was 5 years old. But now I think my experience, at least, is that most people are prepared for women who seem to need, not for women who seem to lead. And why do I say seem to here? Because you may not even be thinking of it as leading. You may just be expressing your opinion. But it's not something that many people like, or some people like. Of course, there's a mix across the board. And in my extensive interactions, especially with girl graduate students, I can tell you that, the first part of the interaction is always very formal. And then once they become comfortable with me, it's always this, this guilt about pursuing my own desires versus, family and other expectations of society. And I've seen, and I've really been sad to see very bright girls either giving up or compromising very heavily on what they can achieve. So yeah, I mean, anyway, I'm very over time, but I've seen this in all my years at IIT Delhi and IIT Madras, right? That there's an enormous pressure that girls feel. And in some cases, they discard these suggestions and rebel against them. Many times they internalize these, right? It's actually, I think, a bit hard not to internalize it because it's just everywhere. And you start feeling guilty for just wanting to do whatever it is you want to do. So yeah, here are examples, right? I mean, it's literally everywhere. So our ads, our movies, and you might think that these are, stupidities like, who cares about Fair and Lovely, who cares about this movie or that ad. But it's actually even in premium institutes around the country, the forms are almost always gender biased, right? So I have filled any number of forms asking me my father or husband's name. And my husband also has to fill asking father's or husband's name, right? So being my husband, he strikes it out and writes wife's name. But the forms are all gender biased, right? A few weeks ago on a walk on campus, somebody met me and said, so are you a faculty's daughter or a faculty's wife? Students are often referred to just as boys. And I mean, if you correct somebody, they'll be like, "Arey, kitni ladkiyan hain, kya farak padta hai?" It captures the majority set, right? It's always Professor X and just Shweta, or not always, I should say, but often. And my husband and I would go somewhere and it would be, here's Dr. Uday and his wife. And in one case, for instance, there was a conversation involving two male colleagues and myself. And the person speaking to me was sort of appreciating the fact that we came back to India to contribute to academia here. And he literally said to me that the future of the country depends on these guys, referring to my two male colleagues, right? And he was actually talking to me, so he could not even parse that I'm one of this set. So society does have biases, and so does science, because science is part of society, right? So scientists are supposed to be objective, able to evaluate data without being swayed. But this is not true, and it is in fact unreasonable to even expect that we should be somehow in such a bubble, sort of so far away from the society we live in. So yeah, there are many things I've heard. Women can't do math. This, I think I heard so much growing up that I many times think that I ended up doing math just because I was so fed up of hearing this. Right? I was actually much more interested in the arts, but that was too much of a girly thing, so I didn't want to do that. Of course, that's not the right way to make decisions. Women are good at rote learning and not reasoning. So, in school, we used to be told this. It is not feminine to argue. So this, again, I have heard really an infinite number of times. Why would Google pay so much to hire a woman who's just going to go on maternity leave? This was said by a colleague at a very top university in the USA. I saw a very beautiful woman on our floor and I said, what's she doing on the science floor? Your paper has better chances of getting accepted because it's an all-woman paper, it will get more sympathy. You left your parents to follow your desires? Our daughters would never do that. If you study so much, who will marry you? This was a fairly fundamental concern that many people had. Women need to put family first. This is, of course, repeated again and again. So what next, right? So is this daunting or depressing? I mean, certainly in a Vigyan Vidushi talk, am I here trying to, pull everybody's spirits down? Actually, in my own experience, I feel that that seeing it is a very powerful tool. So personally, I feel that seeing it helps enormously in overcoming it. It only matters really to the extent that we let it matter. So if we become aware of this, if we become aware that several women go through these challenges, then we understand that this is not something we need to respond to. We don't have to live our lives in this way. And I think that if you reject these suggestions, it doesn't mean getting into a fight with anybody, but internally not accepting these suggestions. If we cultivate the ability to do that, and it's a lifelong process, then they cannot touch us. Do I always call it out when somebody makes a sexist remark? Actually, this is of course very personal. Often I don't. Often I do, often I don't. Because I think that preserving one's creative energy, this is just totally just me. So I'm not, advocating any global way of dealing with these things. Everybody needs to figure out their own way. But I feel that for me, if I don't think anything positive is coming out of it, and if it's going to upset and agitate me more, then I might ignore it and try to just preserve my energy and channelize it to better things. Of course, I also do call it out many times in situations that matter. I definitely try to call it out and take some steps, but it's happening a lot everywhere. And I feel that calling it out every single time you notice it, it ends up, at least for me, draining energy quite a lot, right? And cultivating a support system is really important. So personally, what has helped me and continues to help me is that I'm willing to accept whatever consequences are of the decisions I make, and I'm okay with just following my gut, whether anybody supports it or not, right? And over time, people come around. So there was a lot of resistance even to me doing a PhD. Various things were told to me by various people, important and unimportant. But I said that I'm doing this. Maybe it's a bad decision. Maybe bad things will happen. I can't finish. I can't whatever. And the greatest of all nightmares, that I may not get married. Right? That seems to matter around here. So I said, yeah, all those things can happen. No problem. I'm just going to go ahead. So yes, let there be no looking back. Here is a woman all of us can admire and imbibe from. Life is not easy for any of us, she says, but what of that? We must have perseverance and above all confidence in ourselves. We must believe that we're gifted for something and that this thing must be obtained. That's all I had. I'm very sorry for going so far over time. Thank you all for your attention, and I'll be happy to take any questions.
Thanks, Shweta. That was really wonderful. I'm sure there are a lot of questions from our students. Please go ahead.
So Shweta, if I could, so there were two questions which were on the discussion forum. So one was about PhD programs in general, and the second was about research in theoretical cryptography. So do you want to take a minute just to talk about that?
So what exactly is the question there though? So PhD programs, I think that is great to do a PhD. I think you should come to IIT Madras. Yeah, I'm sorry. Like I didn't understand what to answer in that.
So I think that was Jaya's question. Jaya, do you want to ask the question? Do you want to expand on that?
Yes, sir. So, like you had mentioned, like if we want any general info about PhD program research area, like what research do you do in IIT Madras or something in cryptography? what areas?
So I think that most universities now will have good web pages. So for instance, at IIT Madras, in cryptography, we have this group which we call CCD, Cryptography, Cybersecurity and Distributed Trust. So we have a web page which you can find on my web page, for instance. And in general, you look at the faculty in any given institute, and typically you can find web pages about groups and work that is going on, just if you browse around the website. So for instance, on our CCD webpage, you'll see who all are the people involved, what kind of work they do, and that should give you a very good idea. And this is of course not just for us. I'm talking about our page because I know it off the top of my head, but every university will have this. So you go to any university website and the relevant department, the faculty there, and you can look at what work they are doing. Does that answer the question?
Yes, thank you.
So, Shweta, since it's 7:30,
yeah,
so are there more questions? Could people raise their hand if they have more questions, or? Okay, so Swasti has a question. So in fact, what I'm going to do, if that's all right, is that I'll formally close the session. And so, if people need to leave, students need to leave, I think we'll allow them to do that. On the other hand, if people want to stay back, as long as you,
yeah, I'm happy to be around as long as anyone has anything to ask.
So let's just have a quick round of applause for Shweta, and then we can go back whatever questions people have. Thanks.
Thank you.
Yeah, Swasti, please go ahead.
Hello, my question is related to research in cryptography. So I've seen that there are domains in cryptography that you can go into specific research for, say, lattice-based or factorization or post-quantum cryptography. And then there's also interdisciplinary where you mix cryptography or security in general with machine learning or something. So do we need to decide a specific domain, or when we do research in cryptography, it's general in all of cryptography?
So at this stage, I would say you don't need to make decisions. I think it's good just to be excited about different aspects of the field and explore different aspects of the field. If you decide to go to graduate school, right, at that point you'll choose whatever is the most suitable school for you, and you can see what are the topics that people work on there, right? And then you can take courses in different aspects of the field, whatever courses are being offered, and then based on that you can choose an area. So the PhD itself does require a lot of depth, sort of a depth oriented approach, but I wouldn't say that as an undergraduate you need to already decide anything.
My question was about PhDs only, like, because right now we're not doing any concrete research. We don't have a topic as an, but like, yeah, more generally.
Are you a PhD student?
No. I'm an undergrad student planning for a PhD. So that's.
Yeah, so then I think,
it was more specifically, when do we need to decide on a specific domain?
It'll happen pretty organically. I mean, you get started, right? You take courses, you talk to the people there wherever you are, and you see what excites you the most. And it's also important to see with whom your personality gels. That's also very, very important, because a PhD is a long-term commitment, and you could have somebody whose work you find very exciting, but with whom you're not personally comfortable. So I think that, it's not that there's anything very, made for each other in these things. Like, it's not that there's just this area that I could have worked in. I could have not even been doing cryptography. I could have been doing information theory or graph theory or something else, right? So it's just there is some amount of randomness in the process of choosing your research topic, and I think it's fun that way. Like, so one needn't be very focused on specializing right away. Very organically it will happen. At least this is the way I approached it, that you take a bunch of courses, you talk to a bunch of people, you see what strikes you the best, you see with whom you're most comfortable, and pretty organically you will find the topic that you're looking for, the advisor that you're looking for, and she or he will suggest papers to read, right? And then again, there's freedom that you have. So finding the PhD topic, I think, is a much later stage that I would not say you need to worry about now. For now, it's just good to be excited and learn whatever you can in related areas.
Okay, thank you.
Sure.
Okay, that's it. Then maybe we can actually close the session. Okay, Prahlad has a question.
Actually, this is a technical question. So can you actually show a slide in which you have the final guarantees of the deniable FHE scheme? What's the final?
So we get poly deniability, but we get compact ciphertext. So it turns out I seem to not have a slide on that, because I didn't think I would have time to get to it, but I can tell you. So basically what we're going to get is that we're going to get a detection probability, right? You fix your detection probability, some 1 over poly. Okay, and that poly, your encryption running time will scale with that poly, but the ciphertext size will be compact and independent of the detection probability. Does that answer the question?
Yeah, that's it. So the number, do you put a bound on the number of people you can hold a gun at, or is that?
No. The bound is not on that. The bound is only on the running time of encryption.
Okay.
Yeah. So this also we.
Go ahead.
I was just saying that this also we can mitigate somewhat. So we can do all the hard work offline. The online phase can be independent of the detection probability. But yeah, I mean, we were really trying to get rid of the dependence of the encryption runtime on the detection probability, but instead we showed that it is inherent for this class of constructions.
Okay. Thanks.
Yeah.
Okay. Then okay. So thanks so much, Shweta. Thanks for taking so much time out for all this.
Sure.
And yeah. Okay. I will close the session now. Sorry,